Hello guys, welcome to our presentation. My name is Licheng. Today I'm going to introduce an exciting tool that may help with the frequency issue of your FPGA designs. The problem is that HLS designs often suffer from unsatisfactory frequency. It is a common headache that we come up with a gorgeous and intricate design, but in the end, you found that it only runs at 100 MHz and you have no idea why. It is tough to understand the RTO generated by HLS, and it's harder to identify the cause of the timing issue. This is a long-standing problem that we have been complaining about all the time. First, let's discuss why current HLS tools fail to do a better job. One important reason is that HLS does not know the physical layout of the design. Some signals that look simple and innocent may actually span long distance and become the critical path. In this example, the output of the function foo is passed as input to the function bar. It is reasonable to register the signal only once, right? I mean, they appear really simple. However, there is the possibility that foo and the bar are placed far apart due to other constraints, so more pipelining is needed for the connection in between. Another important reason is that the architecture of modern FPGA poses new challenges to our CAD tools. Current gigantic FPGAs all consist of multiple dies integrated together. Well, this approach surely helps create more programmable resource, but the downside is that the gaps between dies will incur additional delay penalty for signals. In addition, large IPs and hard ASIC blocks are also integrated among the traditional programmable logic. For example, the PCIe IP and the DDR controllers. These IPs are fixed to certain locations and will consume a large number of resources nearby. So similar to the die boundaries, these IPs effectively form physical barriers as well. For the latest FPGAs equipped with high bandwidth memory, the HBM controller is placed at the bottom of the device. Thus, the bottom die is more prone to congestion as all input and output must be routed towards the bottom part. Current HLS tools have barely considered the impact by such architecture features. Meanwhile, for the downstream physical design tools, we observe that the placer tends to pack the logic densely together and avoid die crossing as much as possible. This heuristic, however, often leads to massive local congestion. Here, we show the snapshots of the post-routing situation of two representative designs. On the left, we show a systolic array implemented on the Xilinx U250 FPGA. We could observe that the bottom half of the device is almost unused. Meanwhile, even if two processing elements are logically neighbors, they may be far apart physically, and the data transfer logic in between may be under pipeline. This is because the DDR controllers are at fixed locations, as shown in the figure, and the design must adhere to such constraints. As a result, the logically regular array of processing elements are not regular anymore physically. On the right is the implementation results of a stencil computation accelerator. It consists of 4 processing elements in a linear topology. Even though the topology of this design is very simple, the current choices of the floor planning is far from optimum, and the design directly failed in routing. Although we face lots of challenges in improving the timing quality, there are hidden opportunities. Since HLS takes behavior level code as input, the compiler has much freedom in adding additional pipelines into the design. In this toy example, to pass the output of function foo to the input of function bar, the compiler can freely add more than one level of registers. In other words, for the same given input from the user, the compiler could choose different level of pipelining and adjust other parts of the design so that the overall functionality is still correct. However, it is non-trivial how to properly utilize this advantage. Where should more registers be added, and how many should be added? Can we ensure that the total cycle count will not increase significantly because of our additional pipelining? And will this additional optimization take too much time? These questions remain to be answered. To addressing the timing issue, previous works all focus on coupling at high-level synthesis with downstream steps in a very fine-grained way. One representative work iteratively run placement and routing to calibrate the delay model of HOS. And another work tried to co-optimize placement and HOS scheduling. However, such fine-grained approach could not scale. For example, many of our benchmarks will take more than 1 day to run even one pass of placement routing. Another issue is that the real placement tool may not behave as expected. For large designs, there's no guarantee that an iterative place and route approach could even converge. Now let me present the core idea of this work. We propose a coarse-grained interaction between HOS and the placement step, compared to previous works that adopt a fine-grained approach. In the existing tool stack, the HOS compilation and the downstream processing are completely independent and decoupled. Thus, HOS could hardly know which signal path will belong. Instead, we propose to couple the coarse-grained floorplanning step with the HOS compilation process. With a rough floorplanning of the design, HOS could accurately pipeline those ultra-long connections across the device. Meanwhile, we leave the local signals to default HOS optimization. Such coarse-grained approach reduces the computation burden and makes the approach feasible for even the largest designs today. Here is an overview of our framework, AutoBridge. AutoBridge first performs a top-down floor planning based on the scheduling and the binding results from HOS. Then it adds additional pipelines and generates an optimized version of RTO. The processing by AutoBridge preserves throughput and minimizes the area overhead. Next, I'll introduce more details of our framework. First, we present the floor planning part. To make the process effective while fast enough, we simply divide the target FPGA into a grid of slots and assign each HOS function to one of the slots. To alleviate local congestion, we limit the allowed resource utilization in each slot. The optimization goal of our floor planning is to minimize the total count of boundary crossing. Note that one important difference compared to previous floor planning algorithm is that here it is okay to have ultra-long wires because HOS will pipeline them accordingly. We formulate our method using integer linear programming, and we apply top-down iterative partitioning to divide the design into the target slots. Each iteration divides all the current slots by half and assigns the vertices to the child slots, while minimizing the overall total count of boundary crossing. In our formulation, the number of variables is equal to the number of HOS functions, and the number of constraints is equal to the number of connections between functions. Usually, the optimization process only takes a few seconds, even for some very large designs. Finally, based on our floor planning results, we pipeline those cross-slot wires to get rid of the global critical path. Meanwhile, since we limit the resource utilization inside each slot, the local congestion will naturally be much improved. However, we may get into trouble if we add pipelining without abandon. Next, I will introduce our approach to preserve throughput and minimize area overhead. In this presentation, I will focus on discussing the data flow programming model, and we assume different processing elements communicate through handshake interface. Meanwhile, extension to other situations could be found in our paper. Specifically, to pipeline a FIFO connection between two sites, we could modify the FIFO to assert the full signal before the storage actually runs out. And then we can directly register all signals without causing an error. In essence, this is equivalent to concatenating multiple FIFOs together, but it's much more efficient to get rid of the critical path. What's challenging about the pipelining FIFO interface is that the unexpected latency may cause the design to deadlock or to reduce the throughput. However, it is difficult to statically determine the impact of our additional pipelining on the overall performance. So note that in our situation, the FIFOs connect arbitrary functions that execute in parallel. Thus, we cannot apply some theories that target more simplified model, such as the theory of synchronous data flow. To address this issue, we propose to take a conservative approach by adapting cut-set pipelining. Whenever we want to add additional latency to one edge, we look for a set of edges of the same direction that could split the graph. And then we balance the latency of all the edges. Suppose the red register is added based on the floor planning results. The blue registers are added to offset the potential impact of the red register. In this way, we can safely guarantee that the overall throughput will not be affected. Expressed in another way, cut-set pipelining is equivalent to balancing the latency of every pair of paths with common source vertex and a common sink vertex. Now that adding more pipelines will have an area overhead, one natural and interesting question is how can we minimize the area overhead while making sure that every edge with additional latency is balanced? So in this example, one of the optimum solutions is shown here. Note that edge 27 and 37 can be included in the same cut. So we only need to add 1 unit of latency to other edges in this cut set. Meanwhile, we avoid including edge 16 in any cut set because it is wider than other edges. We propose a polynomial time algorithm to solve the problem. We assign a variable s for each vertex to represent the total latency from the source node to this node. This idea is akin to balancing the arrival time in static timing analysis. Therefore, for all paths from node X to node Y, the difference of Sx and Sy represents the latency of any path in between. For each edge uv, we have the constraint that Su is no less than Sv plus the latency on this edge. Finally, we minimize the total area so that the latency for balancing purpose, in other words, those blue registers, will be added onto the narrowest edge. We use this simple example to illustrate our algorithm. First, we derive all the constraints step by step. Since there is 1 unit of latency added on edge 1, 2, which is according to the floor planning results, We have the constraint that S1 is no less than S2 plus 1. Because there's no latency added to H24, we have the constraint that S2 is no less than S4. The same applies to other edges. The optimization goal is the total area. Note that since edge 3,4 has a width of 2, it is reflected in the expression. Our formulation is a system of difference constraints, which is proved to be solvable in polynomial time. For our largest designs with 500 functions and 1,005 connections, the rebalancing step only takes 30 microseconds. Finally, we present our experiment results. Our benchmarks include a wide range of common topologies in FPGA designs from top conferences. By scaling up and down each benchmark, we test 43 designs in total. On average, we achieve roughly 2 times increase in frequency. 16 of our designs originally failed in routing. We observe little change in resource usage and the total cycle count. Here are the detailed results of selected case studies. For the stencil accelerator, we could observe how our floor planning helped the placer to reduce the suboptimum die crossing. This is because we properly utilize the high-level information about the topology of the design. The Gaussian elimination accelerator, in this accelerator, we can observe that by default, the placer will try to squeeze logic together while we enforce a balanced utilization to reduce local congestion. Meanwhile, the global ultra-long connections are properly pipelined. This is the CNN accelerator. The 16 by 13 array is our largest test case that almost fills up the entire device. And AutoBridge still makes it to over 300 megahertz. Now that we have both pipelining and floor planning, we show control experiments that both factors are needed for the best result. The green crossing represent the result by AutoBridge, and the black dots represent the baseline. First, floor planning without pipelining will obviously backfire because this will introduce long wires while when the tool tries to distribute the design across the device. Second, we run experiments to show that pipelining without floor planning is also not enough, as shown by the blue triangles. This is because the placer does not have the high-level information and that how this additional pipelining will be utilized. And very often, those additional pipelining will be clustered together. Finally, we claim that both the die boundaries and those large IPs, such as the DDR controllers, will be detrimental to timing if we do not treat them properly. Thus, we test the situation where we do not set a boundary at DDR controllers, as shown in the yellow diamonds. Currently, AutoBridge is widely used by other members of our lab to achieve better frequency. I'm proud that the tool has a real impact. So if you like it, please visit our open source repo and give us a star. Thanks a lot for listening to our presentation.